Q, or we're going to find tau at the centroid using box beam. Okay, using box beam analysis. Okay, we're going to use box beam analysis. Okay. So this is the point of interest now, right? So the area we're going to consider, we are going to consider this area. And then we are going to consider this area. Okay. And because it's box beam analysis, we are going to do what? We are going to do 2Q. Okay. So the width, so Q at the centroid will be equal. So the width is equal to, so we had this before, 2 minus by, let me remove this, 2 minus by 0.3. So this is our width. Our depth is 0.2. Our Y bar is, come on, Eugene, what are you doing? The Y bar is equal to 1.5 minus by 0.2 divided by 2. And then we're going to plus the width. So now I'm going to do the web. Okay, so you have left and right web. Okay, and then you have the width is equal to 0.3. The depth is 1.5. And the Y bar is 1.5 divided by 2. Okay, so this will be equal to 1.5 minus by 0.1 times 0.2 times by 1.4 is 0.392 plus 2 times 0.3 times 1.5 times 1.5 divided by 2 is 0.675. So this is equal to 0.392 plus 0.675 is equal to 1.067. 1.067 inches to power of 3. So the shear at the centroid is equal to V over I is constant. You got your Q is 1.067. The thickness now is equal to what? 0.3. So 1.067 divided by 0.3 is equal to 3. Oh, sorry, I forget to divide by 2. Why I have to divide by 2? Because it's what? Box beam. Okay, let me write properly. Okay, don't stop scribbling, Eugene. Box beam. Okay, so 1.067 divided by 0.3 divided by 2 is equal to 1.778 Vy over Izz. Okay, so this is what we get by considering the what? By considering the box beam. Okay, now let's consider the other way. Okay, now I'm going to copy the whole thing. Now we are going to use white flange. Okay, as I said, the answer has to be the same. If the answer is different, we're in a big what? Duda. Okay, so now I cover the what? I cover the top. Okay, so we are now going to determine tau centroid. Okay, using white flange. And your white flange analysis, when it's white flange analysis, we only need to consider Q. Okay, so we know based on our shear flow design, this is how our Q will look like at the bottom part. So the area to consider is this area now. Okay, so we're going to consider, I'm going to divide this into this area over here and the other area over there. Okay, so now I want you to see the difference in Q value. So Q centroid, okay, Q centroid. The width, so I'm taking the smaller flange, okay, 0.7. Okay, the depth is 0.2. So I'm considering this part now, okay, I'm considering the 0.7 and 0.2. And then you have 1.5 minus by 0.2 divided by 2 plus the width is equal to 0.3. This is the web part. The depth is 1.5 multiplied by 1.5 divided by 2. Okay, so this will be equal to 1.5 minus by 0.1 times 0.2 times 0.7 is equal to 0.196 plus 0.3 times 1.5 times 1.5 divided by 2, 0.33. So the Q centroid is 0.196 plus by 0.3375. So it's equal to 0.5335 inches to power Q3. So therefore, the shear of the centroid now will be equal to V over I 0.5335 divided by the thickness, which is equal to 0.3. Okay, which is equal to 0.3. And you know that this is only Q, so you don't need to put 1, but I'll just put 1 for you. Okay, so 0.5335 divided by 0.3 is equal to 1.778 By over IZZ. Did you see this number before? Yes or no? Right, so now you understand the concept of what? Box beam and what? Box beam, you need to consider what? Right plane, you need to consider what? Yeah. It's not difficult at all. I don't know why every university is avoiding this. Okay, it's not difficult at all. Yes or no? It's the easiest thing we have seen. Okay. So now we know that at the centroid, what happens? So tau max, right? Tau max. So therefore, tau max occurs at the where? At the centroid, right? So we have 1.778 Vy over Izz, which is equal to what? So we are given that this is equal to what? This is given to us as what? 10 KSI. So 10 times 10 to the power 3. So Vy over Izz is equal to 10 times 10 to the power 3 divided by 1.778. Okay, so 10 power 3 divided by 1.778 is equal to 5.624 times 10 to the power 3. Okay, so therefore, the shear stress at point A, which is equal to the shear stress at point B, which is equal to Vy over by Izz multiplied by 0. What? 0.98. Was it 0.98? I can't remember now. I beg your pardon. Okay, give me a break. Is it 0.98? 0.98. It is 0.98. So therefore, this will be equal to 5.624 times 10 to the power 3 multiplied by 0.98. So this will be equal to 5.624 power 3 times 1.98 is equal to 5.512 times 10 to the power 3 PSI. Are we clear? Okay. So this one, I say, this is the worst problem that you can get. The next one is again not easy. Okay. So the next question that we're going to attempt, before I attempt the next question, anyone, any questions? Y'all find this anymore? Yes, sir. When you say and next thing is critical, if you pop three, you take how many? Two. Right thing. The thing about this is that as a you have to be able to because in teamwork, the thickness is similar. For white flag or for the normal non-teamwork, the thickness is different. Maybe you forget. I did this. Maybe too fast. This is non-thin wall analysis. At point alpha, can you see where I put the thickness? Yes or no? For thin wall is the one on top. Can you see where I take the thickness? That is the difference. Now the thing is what? When to use thin wall and when to use what? Thick wall. There is no rule. As a structure engineer, what must we do? Oh, I'm not ready to observe. I'm just I'll take it for the different. I got the first one, okay. And the terminal, the first one, let me elaborate. If you want to find, let's say we use non-thin wall, okay, non-thin wall. You want to find at point A for non-thin wall. What area do you take? You take this whole area. Yes, because in non-thin wall, the shear flow is just going from the top to the bottom. There's no left and there's no what? No right. Okay, that's what. However, for thin wall, at point A, the shear stress is equal to what? Why? No, it's the terminal. That is why. Can you see the difference? Right? So that is the distinct difference. Does that clarify your question? Good. Okay. And I believe it's not just him. Right? The rest also have that in your mind, yes or no? Okay? Okay. Yes. So I cannot hold the gravitation. Now that's not the design of it. I want the gravitation, 2 hours, 2 hours. Anyone else? Yes. What is what? Where is tau A equal to tau B? Where? Huh? Where is what are you talking about? Huh? Yeah, ask me here. Then you ask me for tangent. Where? Anyone else? Any other question? Be okay? Yeah. Yeah, this is not a shield. These are all profit. Yes, one more question. Yes.
In the example we showed,
Which example?
like not this one, but the one before.
The one before.
Yes.
Today or now or yesterday or.
Which were the off speed and the white one.
Okay, what about it?
So the maximum shear stresses of the central. So this always be the case or special.
I have to be careful. Check.